Okay, hello and welcome everyone. This is the Ethereum Engineering Group Meetup re-recording of the Proof of Work, Proof of Stake and Proof of Authority presentation. I'm Peter Robinson and please guys, introduce yourselves.
Yep, I'm Rob Dawson. I've been working with Consensus since the heady days of October 2017.
Cool.
And I'm Adrian Sutton. I'm also working with Consensus in the Pegasus Spoke. Been here a month and a half now.
Yep, cool. And I'm Peter, and I've been at Consensus for almost a year. Yep, and working in Pegasus too. All right, so I'm now going to share my screen. I'll just, yep, let's go back to here, go share screen. And desktop 3, I believe, is the right desktop. So that should be this one. Cool. And now if I go into here, I go File, and why is that now? Life's like that, isn't it? It should be presenting. To present, but it's not. It's anyway. Let's not worry about this. Okay, so this is the presentation that we did yesterday, and we'll present based on the PowerPoint slides or the PDF I've got here. Okay, so our consensus algorithms allow nodes in a decentralized network to agree on what transaction should be included in the net block. And so the presentation that we're going to go through here talks about the consensus algorithms that are in the Ethereum ecosystem. There are other algorithms used, say, in Bitcoin and other ecosystems. So we're going to start off. I'm going to talk about proof of work, and then Rob's going to talk a little bit about PoS, and then Adrian's going to talk about IBFT. So Ethereum's proof of work algorithm. So this slide gives us a bit of an overview of what happens. You know, the miners come together and they pull together the transactions that they're going to put into a block, and they also grab what are called uncle blocks. They then have a candidate block that they use to, they set up, and then all the miners are busily mining away trying to solve what's called a puzzle problem. And then the one who solves it first, they publish the proof, and then the other nodes then are able to verify the proof. Okay, so what do I mean by assembling all the transactions? So what you're going to want to do if you're a miner is you'll have a whole stack of transactions, but what you really want to be doing is you want to get the ones that are most valuable to you. And so you'll find different transactions will have been submitted with different, and so you'll choose the to put the transactions which are paying the most. So if you want to have your transaction mined immediately, you put a really high gas price. And if you're happy for the transaction to be mined sometime in the next couple of minutes or maybe an hour, then you put a really, really low gas price. And those gas prices can be, say, multiple orders of magnitude difference. And I mentioned uncle blocks before. So you can imagine you've got 30,000 nodes in the network, and at one end of the network, you might have a miner that would have mined a block with a certain set of transactions, and it's a perfectly valid block. It's off block 100 there, so it's the same height, but it's no longer the longest chain. And so rather than throwing all of that good work away, what you do is you incorporate those transactions in by incorporating that block 101A into 102. And so there's a reward structure set up to do that. So as well, the miners create a candidate block. And so that if you look to the right-hand side here, we've got a cutout of a diagram that actually I found. It's actually about 2 years old. I wish I had have come across it 2 years ago. So hats off Dilly Thomas. So this has got some, essentially they can create all of the information in the block except for the mix hash and nonce just by processing the transaction. So they have essentially where the state root is, and they, where, what the transaction root is after all the transactions have been put through, what the receipts are for the tree of receipts, what the parent hash is, so that's the hash of the previous block. The OMA's hash is related to the uncles. Beneficiary is the address of the miner's node that is doing the mining. So the idea is that they've got that together as essentially something as the input to the overall hashing algorithm for the mining. Okay, so then all miners, all of the mining nodes attempt to solve a puzzle problem simultaneously. So each block period takes 15 seconds, and for proof of work, you've got to find epochs, and they're 30,000 blocks long. So that's about 125 hours. So at each epoch, you change the parameters that you're using for block generation so that you're essentially using up more memory to make it harder. And this is allowing for the fact that over time, computers and CPUs become more capable. So at each epoch, you generate a deterministic sequence. So you start off with a seed value. So the initial seed value was all zeros, and then you do a message digest of the seed value from the last epoch to get the current seed value. And so you can imagine you could generate all of those seed values out into the future just based on values that you've got now. You generate a cache based on the seed value. So the cache algorithm is a time and memory hard algorithm, and it's incredibly CPU intensive. And the idea is that it's quicker, to you can't generate individual parts of the cache quickly. You've got to have it stored in memory. And that's the idea of this algorithm. You then can generate a data set, and the data set, the idea is to be able to quickly generate individual entries of the data set, but the data set's really large. So if you want to generate the whole data set, it takes a while, but if you only need to generate selected entries, it doesn't take too long, because each entry in the data set only relies on 256 entries in the cache. So as long as you've got the cache, you could get parts of the data set on an as-needs basis. So for the full nodes and the mining nodes, they keep the whole data set in memory, whereas the light nodes, they'll generate the data set on an as-needs basis. So all of the nodes are trying to solve this puzzle problem. And so we've said that, as time goes by, the data size gets bigger. And so when Ethereum started, the cache was 16 megabytes and the data set was 1 gig, and it's growing at 128 kilobytes and 8 megabytes per epoch. So that's each 4 days or so. And so we're at that block number, which is epoch 195. So at the moment, the cache is about 40 megabytes and the data set is about 2.5 gig. So each epoch, all of the nodes across the whole network need to change to the new cache, and all of the full nodes and miners will change to the new data set. And so obviously if you're a miner, you're going to pre-calculate all of that data set so that it doesn't slow down your mining operation. So then an algorithm is used which uses information in the data set to try and generate a value. And so it takes as input, you remember how we had the block header that was created? You have a nonce value. So this is essentially the value you try out. So maybe you could choose random values, or maybe you just go sequentially. And then you've got the size of the actual data set. And then you have a callback you use to get values out of the data set. So this is so that you can either have a fixed data set, or you could be getting the data values and generating them on the fly. And so the algorithm combines 64 values from the data set, and which reach 128 bytes wide. And the output of the algorithm is the mix hash and the actual result. So the mix hash, as you can see from this little equation here, is an input which combines the block header and the nonce value and generates the result. And the reason why this is useful is that now, just based on that mix hash, you could check that the result is valid. And so it means that you're tying the block header and the nonce to that mix hash value. So unless, and so you could look in the block header to make sure that block header has the, so if we go backwards a few slides, notice how we've got that parent hash there. So because the parent hash is there, then you could check, do we have the right parent hash? If we do, and it is the immediate previous block, then we know that this generated value here must be recent because it's based on that block header that's got the parent hash in it. So you know that it's not something that someone's pre-calculated a couple of days ago or weeks ago. It's got to have been calculated in the last 15 seconds or so. So this is a way of stopping an attack because now you can just look at the mix hash and calculate that result just based on the mix hash and the block header and nonce. So the miner which solves the puzzle problem first, they get to publish the block. And by solving the puzzle problem, what we mean is that that result is less than target value. And so the target value is set so that the mining period is 15 seconds. So as more hashing power comes to the network, you can imagine that the target will go up. Then say some hashing power leaves the network, then you can imagine the target would decrease. And so the idea is that you publish your result and then you push out your mined block, which includes your nonce and your intermediate value, to all of the nodes. Okay, so all of the nodes can verify the block, but the first thing they'll do is they'll make sure the block header has got the correct parent hash in it, and assuming it does, then what it will do before it does all of the other checks, it'll just quickly check, does this block header and the nonce and the mix hash work out to the result? So that's a very simple and quick check it can do, and then it does the full Hashimoto-like algorithm. So I was going to talk about finality here and do lovely graphs and talk about statistics, but I ran out of time as we were putting this together. So what it turns out is that the finality, so finality means when can you be sure that a block will never be reversed. So you can be sure that no one's going to build a longer chain. And so it turns out it's probabilistic. So you can have a certain probability after one block's been built on top of the block you've got. And then after 2, after 3, after 4, the probability of there being a reorganization which would invalidate your block goes down. But anyway, I ran out of time to put the maths in here. So if we redo this presentation in a few more weeks or months' time, I'll do this, or if we create a specific proof of work presentation, I'll put something in for this. So in summary, we've got a leaderless block creation algorithm, and it's architecturally decentralized. So if one of the nodes blows up or stops working, we're all good. But architectural decentralization is a bit of a different kettle of fish. And so this diagram here, which I've taken from EtherChain, it shows as of about a week ago when we were just quickly putting the presentation together, which nodes were actually mining the best block and which ones were actually creating blocks. And you can see that you've only got a few of these miners are actually creating blocks. And if you've got more than 51% of the total mining capacity, then you could choose to say not mine transactions. You could choose to censor transactions from some people, for instance. So yeah, so though we've got good architectural decentralization, the political decentralization is maybe not what it could be. And there are a whole stack of links. So the original PDF of this is on the Slack workspace for the Ethereum Engineering Group meetup. So yeah. Okay, over to you, Rob.
Yep, so I'm going to be talking to you about proof of stake and keeping it probably at a much higher level to the level of detail that Peter's given us, primarily because the proof of stake implementations within Ethereum are still a work in progress. These Casper is the way that people are talking about it, and the actual implementation details of Casper have been changing quite significantly and still are very much in a state of flux. So in the high level proof of stake and the value that we can do at the moment is just talking about why you'd want proof of stake, how from a high level it would work, and when we think it might be coming in. So let's move across to the next slide.
Okay.
So the first thing to think about is why, and I guess the driving reason and the key thing behind proof of stake is the cost of proof of work. And so if you look at it in terms of energy usage, the amount of work that goes into doing proof of work currently, particularly on Bitcoin, is actually the amount of energy that's used to power many nations. And so that obviously is not a green thing, and being able to have something that is better for the environment and does not cost that much compute power would be a really great solution, and that's something that proof of stake aims to do. The other thing that's listed there is the less centralization. So the mining pools sort of list that we saw earlier, that Peter showed us in that pie chart, that is something that is a cost with proof of work, and a known problem with proof of work, that even though architecturally there isn't centralization, in practice it does end up narrowing down to I guess the sort of three pools can sort of work together, and it becomes a bit more centralized. So by going to proof of stake, we lose some of that centralization that is currently happening with proof of work. And then the final reason is that there's strong economic incentives to do the right thing. So a part of proof of stake is that you need to stake your ether or some sort of financial stake with things. And if you break any one of a number of rules with your stake is removed, and so you lose the money that you put into the system. And so there's I guess that strong, or lose a part of that money that you're putting in. And so that strong economic incentive to do the right thing. The whole reason that you're putting in the money for your stakes in the first place is to get an economic reward. And if you cheat the system, there's also these punishments in place. Okay, so if we look at the next slide, we'll start to talk a little bit about how proof of stake works. And so the idea is that instead of there being miners in the system, there's the idea of validators. And so the validators, their job is to validate the set of transactions, and propose a block based out of that. For a node to be a validator, they will need to lock up some of their coins as a stake. After you've locked up and set aside these coins, so for example, putting them into a smart contract, they will be able to start validating blocks. And so what they can do is when they discover a block with a set of transactions that they think can be added to the chain, they will validate and say that this is the block that I think we should put into the chain by putting a small bet on the block. If the block gets appended, then the validators who were responsible for proposing that particular block will get a reward proportionate to their bets. So we move on to the next slide. There's some more information on the staking and bets. So if they cheat, so if for some reason, if it gets detected within the chain that you've been placing bets on 2 different blocks at the same time, you'll have the deposit that you put in for those bets deleted or slashed. And so the proof of stake talks a lot about the conditions for when deposits will be slashed. And so that's essentially saying that whatever the coin is that you were putting into that transaction, it no longer exists as any coin. So a proof of stake protocol, and part of the hard work in getting a proof of stake protocol right is specifying the slashing conditions. So the example that I mentioned before was having a slashing condition which is set up to stop people from betting on 2 different candidate sibling blocks at the same time. So there's that preventing that essentially stake of nothing type situation. So making sure that when you are staking, you really are staking something and putting your money, I guess, so to speak, where your mouth is. If we look at the next slide. So this idea of these stakes and how much you need to put in, it depends. The original Casper papers and the original proposals have been talking about 1,000 ETH, and so in my world, that's Australian dollars. And when I looked up a couple of days ago, that was about 600,000 to just under $1 million Australian dollars, which you'd need to stake. And then once you put that initial stake in, you can start betting on blocks. So that's something that's kind of a bit beyond the everyman. You need to be prepared to make a big kind of bet on this kind of thing. And so the world that's happening is that there will be, I guess, that idea that there'll still be stake pools, and sort of that idea that people will be able to pool together their ether to have someone that does the actual staking work for them, and you'll be able to get together into a pool and do that. And so there's, I guess, a couple of the early proposals for pools sort of sitting there, and companies that are setting up the infrastructure so that once Ethereum does have proof of stake, they'll be able to do it. I guess the other thing to note with the staking, and I guess we'll start to look on the next slide, which starts to talk about when, is it's the 100 million ether question. It's the proof of stake has been 3 to 6 months away since at least October last year, and the 3 to 6 month window keeps on getting pushed out as time goes on. At the moment, to I guess somewhat complicate the problem, CryptoKitties sort of exploded and really highlighted the need for sharding as well as proof of stake, and the two ideas have now been really sort of coupled together, and so that the size of the design and the architectural change has increased, and so I think it's kind of 3 to 6 months from now, but probably more like 6 months than 3 months would be the sort of my mental model currently. The ETH, which was having the Casper description, so ETH 1101, has moved to a spot where I guess it's probably not going to be implemented. So that, this all said, there's currently, as I speak, there's a sharding workshop going on in Germany, in Berlin at the moment, and so it's quite possible it's not impossible that they'll say, Eureka, we've discovered the way that we want to do sharding, let's start moving now. could happen, but it's probably not super likely that it'll be something that'll happen right away. It's still definitely an active area of research, and lots of smart people are working hard on how sharding is going to work, and how the Casper and proof of stake is going to work inside of Ethereum. So I think the current target that I'm hearing the most about in terms of timeline is that it's targeted for late this year, and it might slip to next year. So that's our bird's eye introduction to proof of stake. I'll now hand over to Adrian, who's going to talk to us about proof of authority algorithms.
Great, thanks, Rob. So what is a proof of authority algorithm? Proof of authority is basically a category of consensus mechanisms where the permission to create new blocks is granted entirely based on who you are. It's not based on the fact that you've done work or the fact that you've staked money. It's just, we know who you are, we trust you to create blocks. Typically that's done by having a pool of nodes that are authorized to create those blocks. So that if one of them's down, others can take over, that kind of thing, and possibly have some fault reliability in different ways there. And then the other key characteristic is that there's some way to verify that a block you've received synced via the ETH protocol was actually signed and proposed by an authorized node. That's typically through some form of cryptographic signature. So if we go to the next slide. The other way of looking at this is to look at what the cost of bad behavior is. If you are proposing rubbish blocks in proof of work, it generally won't get accepted to the chain. You've wasted your CPU cycles. And you have to spend a lot of money in getting enough CPU cycles to be able to find the right answer to the crypto challenge. For proof of stake, we burn money much more directly. You literally put up money, and if you do the wrong thing, it's slashed. For proof of authority, what you're effectively burning if you behave badly is your reputation. So you're allowed to create blocks based on the fact that you're trusted. And if you then demonstrate that you're not trustworthy, that can be taken away, and usually results in things like people not wanting to do business with you anymore. You see examples of this in a lot of different places. So for example, Airbnb is basically a reputation-based system. If I advertise my house as somewhere you can stay, and you come along and it's not like I advertised, it's a really rubbish experience, you're going to leave me a bad review, people are going to know not to deal with me in future. So I've burnt my reputation by doing the wrong thing there. And Airbnb itself is acting as a central authority, so that if they get enough complaints that my place isn't suitable, then they kick me off Airbnb altogether, and I suddenly lose entire access to the system. So proof of authority kind of depends on both of those factors, where we want to know who you are, so that if we kick you off, you stay off. We don't want to end up like comments on the internet where you can create a new profile quickly and easily, and so you don't care about reputation. And we have to have some value attached to that reputation. So some way of punishing you and having a negative effect if you have a bad reputation. Usually just, we're not going to do business with you anymore. So looking at when chains are most appropriate, when proof of authority is most appropriate, the most common case by far is on private chains, particularly within consortiums. So a number of companies working together, they know who they are well, they know which company is operating which validator node, and if it starts misbehaving too regularly, then they can remove that company from the consortium and stop doing business with them. But there's a couple of more interesting cases. The Rinkeby test network is a publicly available test network, which was created because the previous proof of work test network got swamped by people submitting a lot of bad transactions, or a lot of transactions that took up a lot of time. And they could do that and afford to do that because Ether is free on a test network and has little or no value. So Rinkeby uses proof of authority to give it a bit of centralization. The people who are running the Rinkeby network are all the validators, and they can choose to censor bad transactions. If they see a user submitting transactions too fast, they can delay mining those transactions into blocks. or they can outright ignore just transactions that look like they'll harm the network, that are deliberately set up to be malicious. And the third one is the proof of authority network, which is a sidechain for Ethereum. And it takes an interesting approach in that it's a public network for stuff that's meant to have value. It's not just a test network. And their validators are required to have a US government issued notary public license. So what they've effectively done is outsource that trust model to the US government. If the US government says you're a good person and says this is who you are and that you're a good person, then you're allowed to be a validator. And you've got to publish that license in a way that other nodes can verify. How much trust you put in that is up for debate and will depend on what you're doing. Obviously, if you don't trust the US government, it's not going to be any use to you. And there's kind of questions around how you revoke access. If all you needed was a notary public license, then it's unlikely that you could complain that they were censoring transactions when they're mining on a side chain of Ethereum and have the US government actually pay any attention and revoke their notary public license. That's probably not going to escalate to that. But if there's central authorities that we can all agree not to allow those people to be validators just because we can identify them, then it can be quite workable. So you regularly see these kind of trade-offs in proof of authority, where you're really just making a decision of how much trust do you have and how much trust do you need. If we look at why, the most common reason is just higher throughput and lower cost. So compared to proof of work, we don't have to burn all those CPU cycles, much lower cost and less resources required. And because of that, it's much quicker to mine new blocks. You can generally do them closer together. Most proof of authority algorithms are set up to try and minimize the number of network hops required and interactions required to get to consensus. And there are different trade-offs involved in that, but that generally allows you to mine blocks quite fast. And so you get higher throughput on your transactions and often lower latency as well. Depending on the algorithm, you can have either just faster or immediate block finality. Generally with proof of authority algorithms, the finality isn't just probabilistic like it is with proof of work, but within a certain number of blocks. Now that's not a guarantee, different algorithms can do different things obviously, but with something like Clique, you're generally getting consensus pretty quickly within 2 or 3 blocks. You'd have a very high degree of confidence. And especially once you've seen each validator, so the number of validators, you'd know that they've all accepted those blocks. But for something like IBFT, you know that as soon as a block is minted and on the chain, then it has immediate finality. It will not be changed again. And finally, unlike proof of stake, you can use proof of authority even when your ether has little or no value. It's not dependent on that because it's purely based on the reputation. So one simple example of proof of authority is Clique, which is simple but effective. In Clique, you have a set of validators that are agreed on. Any validator can create new blocks. It's set up so that they're intended to be round robin and priority is given to someone who is proposing in turn. But the only actual restriction or hard and fast restriction is that, that there is a limit on how often any one proposer can create new blocks. The interesting thing in Clique is how they add and remove validators from the pool. They've co-opted a few block headers. And so when a miner or when a validator proposes a block, they can include the address of another validator, either one they want to add or remove, and they put that into the miner or the beneficiary header, sometimes called Coinbase as well. And then they use the nonce field header to indicate whether they want to add or remove. And as soon as you've gotten half of the validators voting one way or the other, then you make the change to the validator list. So you have the ability to update your validators as the chain goes on, which is obviously really useful. If someone's acting badly, you can vote them out. If you expand a consortium, you can add in nodes from the new company, that kind of thing. And there's a bit of an optimization in that at each epoch, the outstanding votes are reset so that at each epoch, you just have a list of validators. That's the only state you need, and that's in the block header. So you can much more easily go back to the start of the epoch and work forward to work out the state you're up to in terms of votes. But what Clique doesn't do is have any kind of fault tolerance. For that, you tend to talk about the Byzantine fault tolerant algorithms. And that's based off of a paper from a while back, which is Practical Byzantine Fault Tolerance. They used this particular three-phase commit algorithm to build an NFS client that could handle faulty nodes in a distributed way. And Istanbul BFT or IBFT has taken that research and applied it to the blockchain. So with IBFT and PBFT, as long as you've got strictly less than a third of validators that are faulty, then the network can continue functioning normally. Now, faulty includes offline, it includes buggy and actively malicious. And it's quite common that actually the bigger concern isn't so much the actively malicious, which might happen if you get hacked, but just that nodes go offline regularly. Things can be buggy. There can be problems in implementation. You don't want that to take down your entire network just because one machine has gone offline. And so with BFT, you have a lot of fault tolerance in there, in addition to the confidence that even if one node, or as long as it's less than a third of your nodes are hacked, then your system continues working. So if we go to the next slide, this is the state diagram basically for IBFT. It's taken straight from the EIP 650, which kind of lays out how IBFT works. I won't go into full detail onto it, but it's essentially a three-phase commit. So the proposer will send out a pre-prepare message and it goes into that pre-prepared state. Each validator that receives that sends out a prepare message with the same hash of that proposed block. And that's basically saying, yes, I've received this block. This is what I'm planning to insert on the chain. Once they receive 2F+1 commit messages, where F is the number of faulty nodes you can tolerate, so essentially a supermajority of more than 2/3 have agreed that this is the node we're going to try. They then send commit messages to say, I've received acknowledgement from everyone that that's what we're going to try. Again, you wait to receive 2F+1 or greater than 66% of commit messages so that you all know that you're working on that same block. And then you finally actually insert the block. There's a few ways that could go wrong. Either the proposer isn't there. Usually the proposer is selected on a round robin basis out of the validators. If they've gone offline, then you'll reach a timeout and need to try again, and that's where it goes to round change. The same thing if you don't receive pre-prepare messages or prepare messages or commit messages. Anyway, there you can reach a timeout. And to keep the system moving, you broadcast a round change message, which is basically saying, I'm trying to abort our attempt at consensus for this particular block, and I'd like to try again, start from the beginning. And as long as you get more than 2/3 of the network agreeing that it's time to round change, then you do that, you go back to the start of the round, a new proposer sends out a proposal for a new block. The only other real detail there is, if we go to the next slide, is that for a particular corner case of safety, IBFT locks blocks. So once you are prepared on a block, once you've got agreement that that's the block you're going to insert next, even if you go to round change at that point, you refuse to accept a pre-prepare for a different block. It kind of involves a malicious actor sending different messages to two halves of the network, and just eliminates the possibility of a fork in that case. I'll leave you to look up the details in the papers themselves, but I won't try and prove that. But basically, you only unlock on a block when it's actually inserted into the chain, because you're moving to the next height, and obviously you pick a different block. Or if you can't insert, if you get to the point where you insert it and it turns out not to be valid, the transactions fail to apply, then you round change and pick a new block. And that's an overview of IBFT and proof of authority.
Well, thank you, Adrian. So I hope you all of you watching this video have enjoyed this quick summary of proof of work, proof of stake, and proof of authority algorithms. So we tried to put together a slide which tried to summarize how they all worked together. And so for proof of work, and looking at them, one way you can look at them is finality. So when can you say the block is ready to go? And you can reliably say that the transactions in that block are never going to be revoked. And for both proof of work and proof of stake, it's probabilistic. So you're never going to be 100% certain. You might be 99.99% certain, but you're never going to be 100% certain because it's probabilistic. For IBFT and Raft, though, these PoA algorithms, invariably they're instant. Another thing that's interesting is the ability to handle malfunctioning or missing or malicious nodes. And so for PoW and PoS, it's generally less than 50% have to be in that category. Whereas for IBFT and Raft, or rather IBFT, it's around, just under a third. And for Raft, it can't handle any. So Raft is a distributed systems algorithm for gaining consensus that we haven't talked about, but it's a good reference point though, because it is another one of these authority systems where, which you could look at and is similar to IBFT. In fact, if you look at Quorum by JP Morgan, it originally came with Raft as a possibility, and now IBFT is the preferred algorithm, and it's because of this feature about how many malicious or malfunctioning nodes can be handled. And not handling any malfunctioning nodes is obviously a massive problem because it's not the real world. In the real world, things do malfunction. So there's also the trust level that's involved. And so for proof of work, it's trustless. So you don't have to trust anyone on the network. And for proof of stake, the goal, the design goal is it's got to be trustless because the whole aim is to replace proof of work. IBFT, you need to have some level of trust, but you don't, if IBFT is good for, I guess, consortiums where, you can imagine as well, you might have at what point do you not fully trust all the nodes on the network or all the organizations on the network that have got nodes on the network? If you've got 10 nodes on a network, maybe you know everyone and you trust them, but maybe once you've got 1,000 nodes on a network from 1,000 different companies, you don't know them all well enough to fully trust them anyway. So having an algorithm that works with some level of trust but not complete trust is good. So Raft, it relies on all nodes being trusted. And of course, energy usage is a big one. So obviously for proof of work, you've invariably, I'm sure you've all seen those photographs of factories full of computers just burning electricity, solving puzzle problems. And so that energy usage is huge, whereas the other algorithms, it's quite low. So for those of you attending the meetup, we're not going to have one in 2 weeks' time, but we will have one on July the 25th, and that's going to look at advanced solidity and design patterns. So it's how do you design your solidity code and your overall sets of solidity code, and the advanced solidity is really going to look at how do you have set it up so that your gas usage is either flat or linear based on the data that you're putting into your contract, and also looking at advanced things like doing calls to the elliptic curve functions and the modular exponentiation functions. So essentially the precompiles and how do you get that to work. So I don't have to ask if you've got any questions, so thank you everyone for joining the call or watching this, and please hop on to the Ethereum Engineering Group meetup Slack workspace and fire questions in there in the general channel if you do have questions about this video, or you could, I guess, even put them onto YouTube as a comment as well, and we'll get back to you about any questions you do have. So thank you everyone, and have a great morning, day, evening. Thank you. Bye-bye.
Thank you.